Let me invite our next speaker, Bob, up here. So Bob was just hanging around the plasma fusion lab at MIT when I met him. And Bob and Dennis White, his boss, just really inspired me with some very simple sounding ideas on how you could completely change all power generation on the planet. Complete loon shot, but very, very exciting. I thought to myself, this is too important to not try. It doesn't matter whether it succeeds or not, or what the probability of success is. It's just too important to not try.
It does matter to some people.
Huh?
It does matter if it succeeds to some people.
Well, I always say there's a whole bunch of entrepreneurs who are doing things that are so important that you have to try them. And as I say, I'd rather try and fail than fail to try. We are very far along from there now. But, people have been skeptical of fusion. The running joke is it's 30 years away, and it will always be 30 years away. But tell me what got you thinking differently about fusion?
Yeah, so I'd say
maybe start with what you're actually building.
Yeah, so why do you do fusion? Like, why does fusion end up in like science fiction and things like that? And I think that's been the thing that's really been clarifying is the climate crisis. So you've got the climate crisis, like that's fundamentally we have too much carbon in the air. Like, how did it get there? Well, we dug up a bunch of it and we put it through a reaction that made CO2, and that's like the most prominent reaction in the world, and that's how we powered our entire society, like 50 gigatons a year. And that's got all these big downsides. But fusion's been out there as this thing that is a completely different reaction, right? It's a reaction that's 200 million times more energy per reaction than coal. And so it's really an interesting thing. Like, we used to think the stars were 5,000 years old, because that's how long they would last if they were made out of like coal. But once we found that they were made out of fusion, it meant that they were 10 billion years old. And so if you could do that on Earth, it'd be this big deal, and you'd go from a world where you were consuming resources to a world where you just had energy from a machine. And people have been searching for that for like 50 years, trying to build machines that can create the same reactions, the same conditions inside the stars, but on Earth that we can control. And if that were to work...
A little reactor.
Yeah. And so they built...
I still vividly remember I stepped on this vessel reactor, and Bob said, a few minutes ago, this was 600 million degrees below you.
Yeah. So like, you have to build like a star in a bottle, right? It's like, not even like that's not an analogy. Like, literally what it is. Like, so you have to build this machine that can create the conditions that the stars do. And we've been doing that scientifically in very large national labs and universities for a long time, and we've actually been making really good progress to make that reaction happen. It's faster than Moore's law in almost every parameter that you could look at scientifically. And we're like sitting there within a factor of a few of making it useful, of actually making the reaction so vigorous that it takes more power, it makes more power than it takes to actually start the reaction. And the world was on this trajectory to like get that done in like 2050, which is a little bit too late for climate. It's actually quite a bit too late. And so what had happened at MIT is we stumbled across a technology that was completely unrelated to fusion, that if it could be developed quickly, could be applied to fusion and change that trajectory, basically bend it into nearer term. And it was a technology that someone mentioned earlier about superconductors. It was a new material, so this is like something that came out of material science labs, not out of like physics labs, like where we came from. And if you could do that, you could take all the science that we'd done to that time, and all the demonstration that we've done in machines like at MIT and in France and the UK, and you could put it into something that was like a product, something that was economical, something that you could demonstrate soon. And it was at the right scale that you could think about, well, you might be able to actually do this commercially, you might be able to do this as a company. So instead of doing it as an international collaboration of scientists, could you do it as a company? And it was really a confluence of a bunch of events: that material, the science from the fusion side, the climate poll, the position that MIT had found itself in terms of having a bunch of talent all together, the funding market as it was coming back from like Clean Tech 1.0, all at the same time in 2015, 2016.
Mm-hmm. So the ITER project is the multi-nation, how much is it now, 20 or 40 billion or something?
It's like 50 billion now.
$50 billion project. And Bob decided it was possible to compete with that project. That'd be done by 2050. Tell me what made that possible, why you thought you could take on something with 1/50th the resources, or back then you didn't even have $1 billion. What made it possible?
Yeah, and this goes to like, you're trying to do something new. You have to like the fundamental principles. And so in these fusion machines, the fundamental principle is they're basically magnetic bottles. They hold the star stuff with magnets. And they need to insulate that very, very well. And you have like 100 million degrees in the center. It's the hottest thing in the solar system. Like our machine at MIT is literally the hottest thing in the solar system. And then like a meter away, you have like room temperature. So very well insulated. And that's because of the magnetic field. And it turns out that the magnetic field, the sort of power of a fusion machine goes like the magnetic field to the 4th power. So it's like this huge lever, right? And we'd shown that over and over again, that if you just change the magnetic field a little bit, you could change the size of the machine by quite a lot. And everyone had always been up at the edge of the magnetic field they could build with technology. And so what we did is we took this new material that was a new type of superconductor that eliminated a limitation on the magnetic field that had existed before. And we said, we think we can actually get enough of this superconductor together, and we can actually build a magnet that's twice the magnetic field than anything existed before. And so a complete step change in like the 300-year history of magnets. And at twice the magnetic field, you could then take a machine that was like a large multinational machine like ITER, which is the largest construction project in Europe, and you could put it, instead of like on a stadium, you could put it in like a garage. And that's the type of big shift that you look for in a new technology, right? It's like not an incremental thing. And we went to the scientific community, very transparent. We published, we collaborate with everybody, and said, hey, what do you think of this idea? And the conclusion was, yeah, if you had that magnet, that machine would work, and it would be that small. And we don't see any showstoppers except for that magnet. And so that's laid out a very, very concrete plan to do risk retirement in this field that people had worked on a long time, of first build the magnet, then apply it to that machine, demonstrate for the first time ever that you make more power out than in from a fusion reaction on Earth. And then that is a product and a power plant that we know how to deliver. It's a way to boil water, the same way a coal power plant or a gas plant is, but it's using a fundamentally different reaction.
So how long do you think it took ITER to build their magnet?
Yeah, so we actually just did a study on this. We're running at about 10 times the speed of ITER. And so whether that's in how fast it takes us to build a building or how fast it takes us to develop a magnet. So it took ITER about 25 years to develop their magnet technology.
It's a very old project.
Yeah. This is like the scale, like the Large Hadron Collider, right? It took about 25 years, and we were able to go through all the same stage gates in just over 3. It was one of these things that one of our physicists was just giving a talk at the main plasma physics conference, and middle of the talk, standing ovation, like spontaneously when they talked about this magnet.
That's awesome. This is why the world needs entrepreneurs.
Yeah.
And only entrepreneurs can change the world. But our first task was then making the magnet, and we had to raise money. We used a very entrepreneurial pitch. Said, if fusion doesn't work, what would happen to the $100 million you had to raise to build a magnet?
Well, it turns out that the magnet was useful for other applications. And so it's useful for things like wind turbines or things like MRI machines, or things like generators. And so we were able to line up a bunch of different applications that said, hey, this isn't so binary. That, yeah, it's new, it's novel, but it has this big upside of fusion. But if it doesn't quite go right, like, we've still really advanced the state of the art in these other areas. And actually, we're just shipping a magnet to University of Wisconsin that's unrelated, out of the same program.
And so how long did it take you to build your magnet?
So first, we broke a lot of things. So it's like, we built stuff, and you're at the cutting edge, and so, like, just build it, test it, test it, test it, break it, build the next one, and build that cycle as fast as possible. I remember we were going to a big national test stand in Switzerland, and we called them up and we said, hey, we want to show up and test every week. And they said, no, people test every year. I said, no, every week we're going to show up with a new sample. And these are like big samples. And they didn't take it seriously, so we said, what's your operating budget? We'll pay for the entire year. If we don't use it, you can have the money. And they said, okay, fine. And so we showed up every week and just threw things through their test stand, pushed them to failure, took them out, smoldering thing, looked at it, took it apart, said, okay, called up back at MIT and CFS, build the next one. And so through about 20 iterations of that at subscale until we got confident enough that we had the technology, we could go to full scale. And then we went like straight to full scale, so not intermediate. Like, okay, this thing's got to work at this scale. It's got to be 10 tons. It's got to carry 10 million amps of current. It's got to have the most superconductor in it that's ever been put in this by a factor of 100. Let's just try it and do it. And we built that magnet. It took us 2 years to build the full scale one, which is like still, why did it take so long? It takes long to cut metal. It's like, damn it. Why can't we cut metal faster? All the AM companies. And we eventually, pretty much on budget, on schedule, got the full-scale magnet. And it worked straight out of the box. We live streamed it to
about
everybody.
3 years?
Yeah. The subscale R&D was about a year, and then the magnet, the big build, was about 2.5.
So
we still build
last
them.
Labor Day weekend was exciting as we watched the magnet come up to 20 Tesla slowly. Yeah. It's a long time.
Yeah. It's like, a day-long party of everyone that built it, watching on pins and needles, and we live streamed it to a bunch of all the stakeholders and people had the link of Tesla by Tesla by Tesla. It was a 20 Tesla magnet, so 20 Tesla. An MRI machine's like a Tesla and a half. So this is like really, really high field.
So you've eliminated the key risk, which was, can we build a magnet? What risks remain, and where are you? And tell me, when will we know?
Yeah,
this actually works?
So one of the techniques that we really thought about was, you have this new.
So I just had to set the stage. ITER started 25 years ago. They expect to have prove that they can generate more energy than they consume by 2035.
Yeah,
roughly.
They're going to be late, but yeah.
So you started 3 years ago. When will you prove this?
25. So. So right now we are in the act of building a machine. It's called Spark, and it's a fusion machine. It easily fit in like half of this room, and that machine, is part of a building. It's all first of a kind type stuff. It's a project hour outside of Boston. It's got about 1,000 people that work on it. It's about $800 million project. But it'll be a machine that in 2025 you push a button, and for the first time on Earth, you will make more power out than in from a fusion plasma that's about 200 million degrees. Cooling towers will have a bunch of steam go out of them, and you let your finger off the button and it will stop. And you push the button again, it will go. And like that's a new paradigm for an energy source. That's like lighting light bulbs with fission the first time, or fire, or things like that. And so that's something that the world's been waiting for since we basically understood how the stars work.
Yeah. Well, it is very exciting. Now, you'll prove this, but what happens next?
Right. So that's still like a demonstration. And I think this is one of those things that these really big problems, you think about like big problems that we all work on. Like I work in energy. 1 out of every $13 that's spent is not spent on energy. It's 10 million people that work in that field, right? These are huge problems. So just having a proof of principle isn't enough. You've got to be able to make it into something that is like infinitely replicable, that has deployment models that can be scaled around the world. It can't just be this one-off scientific jewel, right? So everything that we've done is to build it so that we could build 10,000 of them. So when you're in like a meeting at CFS about how we should, design the magnet, someone will say, how do you make 10,000 of them? Because if you make 10,000 fusion power plants, that's enough to be about half of the global energy use. There's about 60,000 power plants in the world today. And that's what you have to do for climate. By 2050, you have to do that, otherwise the world burns. Doesn't matter if it's fusion power plants or solar power plants or whatever. There's that many of them. So there's like, you have to go out and be able to build them as if they're Walmarts or build them as if they're like 737s. And so you start with that in mind. And you say, okay, that means we got to make this thing into a product that is as simple as it can be, that can be built by as many people as can build it. And we have to go as fast as possible to show it works, and then it can be made. And so we'll do that in Spark. And like even in Spark, even though it's a demonstration, it's built by like a regional constructor, someone who's used to building like Amazon warehouses, not by like a very specialized fancy firm from the construction, for pouring concrete. It's like built to scale. And then we'll move to Arc, which is a little bit bigger, about twice the size. And that will be about 200 to 400 megawatt plant. And that's the scale that is a lot of the coal and gas plants. And so that means you could have a model where you show up where there's a coal or a gas plant, and you build this machine, and you hook it to that grid connection. So now you're replacing something. You're not having to reformulate the entire regulatory regime or the entire model in which we like finance power plants or anything like that. You're co-opting all that infrastructure, but you're just changing the reaction inside the machine. And so that machine we hope to start. Maybe we'll start it in parallel to Spark. We're not quite sure yet, but turn it on to our 2030.
So, explain this concept of a fusion boiler.
Right.
Versus a fusion power plant. We've talked a lot about it, and
yeah, so it sounds like really crazy, right? Like you have like fusion, and it's in like Doc Ock, like comic book stuff, right? But at the end of the day, it's just heat. You're making heat the same way the sun makes heat. You have to capture that heat and turn it to work. And it turns out like we've been making heat to work since Watt, right? And so it does that the same way. It's, you make literally a fusion boiler, except instead of being heated by the combustion of carbon into CO2, it's heated by the fusion of hydrogen into helium. And out of that comes a pipe, and out of that pipe comes like 650-degree heat in the form of moving fluid. And in our case, it's molten salt, but it could be steam, it could be other high-temperature helium. And that goes into a heat exchanger, and eventually makes steam, and eventually turns a turbine. And the good news is that we know how to do that. Like 90% of all the energy that we use today, that's exactly how it's done. And all that infrastructure is already there. It's already sitting there. It's been refined by 100 years. And so the fusion power plant, is like the whole thing, but really the innovation is in the boiler part. It's in this machine that makes a bunch of heat using this reaction.
So power plants have very long lives. We got quite a few in the US, probably 5,000 coal plants or natural gas plants. Those have 50-year lives. These are businesses. They hate the idea of having to shut them down, obsolete them. How do you help them? How do you get them on your side instead of fighting you in Washington?
Yeah, well, the first thing is to realize, like in almost everything that a crowd like this does, there are a lot of stakeholders. Like if you want to change the world, like turns out your stakeholders are like the entire globe, and so you got to like factor that in from the very beginning. And in the case of a power plant, the stakeholders are the people that own it. They're the people that live near it, the people that work at it. They are the people that supply it with goods and services, whether that's fuel or parts. And so they have to be a part of this. Otherwise, you're fighting a very, very big uphill battle. You can't show up and build a power plant in a community that doesn't want it. It's just not going to work. And so that means it's not just the technology, it's actually all the other pieces around the technology that you have to get in front of. And if you're out there like building an entirely new industry, you literally have to like write the rules of that industry. So we had to, for instance, go to the federal government and write what we think the regulatory rules for this technology would be, and pass legislation to get those rules as the rules. And then we had to go find communities that wanted this. And so well before we ever decided where to build Spark, and we were out in many communities around the United States asking, hey, what do you think about this? And trying to find places that were very excited about it. And we ended up finding one in Devens, Massachusetts, that is like, understands technology, very concerned about climate, high-tech jobs, and they were like, yes, let's do this. Let's put this right next to our watershed for our river and show that this can be done in an ecological, safe way. And then also like on the people that own power plants. So we looked and said, who's going to lose in the fossil fuel transition? It's like, well, it turns out there's a lot of money in big oil companies. And so, what's their plan? And we went and asked them, like, hey, what's your plan? And like, well, we have a gap. We're not quite sure what this looks like. And like, well, come learn about fusion. And through a couple years of talking to them, a couple of them, probably the most progressive ones, they got really excited. Like, we could actually see a future here where our expertise of how we build pipes and how we build projects and how we run platforms, that expertise could actually be used to scale this technology. And they became some of our biggest advocates. And so we're the largest investment in ever for Eni and Equinor, the Italian and Norwegian oil companies. And that also means that they're in Washington, right alongside us, right? Saying like, this is what the future of energy should be. This will be zero carbon. We want to be a part of this. Let's go forward. The power plant owners, likewise, like they don't want to write off those assets. They're going to be forced to stop running those fossil fuel plants because they can't emit. So what do you do with that land? What do you do with that infrastructure? It's like, well, if you had a technology like this, that would be a really, really big deal for them. It means that community still keeps jobs. It means that community still gets taxes for making energy. It means that the site and the infrastructure continues to be reused, and it can stay on the books as a profitable thing for that business. And so by pulling all those in way earlier than what you would normally think, like don't wait on a go-to-market strategy till after you have the product. Like pull them in really, really early, and then build a coalition. And then we've been able to do that with pretty good success.
Yeah, I thought this was brilliant strategy. Instead of all the pressure on every coal power plant to shut down and write off their assets and basically be out of business, to say, we'll just build you a new boiler, which is replaced regularly in coal plants anyway. It's the part that needs the most maintenance. And you cut your time to build a power plant in substantially, no regulatory, no permitting, or minimal permitting. I thought that was brilliant strategy.
And like the local community doesn't have particulate emissions anymore. There's fewer trains delivering coal. There's a bunch of benefits. Actually, the one that we haven't figured out how to get them on board is the train companies. Like the train companies end up not winning. So if anyone has ideas, see me.
So there was a surprising piece of research I did about 15 years ago and wrote a paper on this energy transition. Most people don't realize that around coal plants, there's more radiation because of the ash that goes up in the air, and more radiation deaths than around any nuclear power plant, period. So the coal power plants are radiation hazards, and you get to avoid the problem. But let's be optimistic, or you might say pragmatic. So we build a power plant in the next 7-8 years. In 2030, we have our first one operating. How do you replace all 5,000?
Yeah, and this is a general problem with anything that's fighting climate. So like most of what we do in entrepreneurship, like your timeline is set by maybe the cost of capital or maybe your competitors. There's like some social dynamic to it. In climate, the timeline is set by a molecule that's in the air. Like it doesn't care what we do. Like the world is going to continue to heat. And unless we stop putting more of those molecules up, it will get really, really bad. And like you have to stop by 2050. And so no matter what you do in climate, if you're going to displace fossil fuels, you have to be able to build that at a speed that is not like we've built anything like that before. It's a speed that's closer to like the way we've rolled out cell phones than it is the way that we built even wind or solar. It has to drastically accelerate. But the good news is that we know that's doable. Like we have instances in history where we've done that, whether it's like building the Liberty ships for Arsenal for Democracy in World War II.
Talk about the Liberty ships example.
Oh yeah, it's like you think about how much work it is to build something really big, and it's usually very slow. But turns out, like once people got organized and said it needed to be done, they figured out how to build ships, thousands of ships in Los Angeles, like an assembly line of ships to fight World War II. And they took Ford from making automobiles to making way more complicated Boeing bombers. And that was because like Boeing adapted how they would make those bombers so that Ford could make them. And so there's this huge industrial base that exists that can be co-opted to do these types of problems. And it's been done several times in history, even in energy. It's like, France actually decarbonized their grid. France is completely decarbonized. They decarbonized their grid in 10 years. In the 50s, and they said, we're just going to build nuclear power plants, and we're going to stamp them out as if they are products, as if they're not one-off stick-build things, as if like they're all the same, and here's the foundries that make the parts, and these are the people that go and install them, and just go from site to site to site to site, and they've been able to do that. And they supply electricity to almost all, a lot of the clean energy in Europe comes from that fleet. So
here's the numbers. Before the Second World War, the U.S. had built 10 Liberty warships in the decade before the war started. Not far from here, the San Ramon Iron Works was started, and in the next 5 years, and Liberty warships are complex beasts, in the next 5 years, during the Second World War, the US built 4,600 Liberty warships. I think we have a shot at building 4,600 fusion boilers, which are simpler than Liberty warships. So it's the most optimistic story I've heard on climate. I definitely wish you great luck, because if we're going to solve the climate problem, and most people give up and talk about how it's not possible, I think there's a ray of hope here, frankly, more than a ray. It's real optimism, because I think it can be done. Thanks very much, and we'll break here.
All right, thank you.